Hey everybody, this is Tyler with Arima Security Research, and today what we're going to do is go through one of the articles that I wrote published in Toward Data Science on Medium called Predict Home Runs in the World Series with R. So before we get started, there is a link we should take a look at, which is either the Medium article itself or the post up on the Arima Security Research website. And what we're going to do is work out of that file and out of that article and work through the project together. So let's jump into it. So the overall idea here is that we're going to use generalized linear models to try to predict how many home runs happen in a World Series based on a set of conditions. So we're going to use some publicly available data and a few techniques and get into it. We're going to start by learning how to import data without loading it from a local file, which is pretty handy. We're going to split our data into test and train data sets. We're going to use data that is not normally distributed, which is going to be fun. And we're going to create logistic regression models and also walk through the stepwise regression method. And then we're going to use our model to make predictions and see how accurate we were. So first thing that we're going to do is use Sean Lahman's data. You can take a look at the website. It's linked in there. They have put quite a bit of effort into that, and it's some pretty good data. Now, I'm not the biggest sports person in the world, but we can work through that together and find out some cool things about home runs. So first thing that we're going to do here is open up RStudio, whether you are in a Windows or Mac environment or maybe even Linux. Open up RStudio. Up in the top left corner, we're going to open an R Markdown file. It's the white page with the green and white plus sign logo. We'll go ahead and click on R Markdown. I'm going to call this baseball and go ahead and hit enter. So if you've seen the videos before, you know what I'm about to do. If you're new here, when you open a new Markdown file, you get all this junk that's here. You don't need that. Highlight it, delete it. Doesn't need to be there. When you want to add a new chunk, go up here to the big green C with the plus sign logo. We're going to add a new chunk. Go ahead and click on R, and we're going to load up our libraries. So I'm going to be just copy pasting code out of that article, so you don't have it handy. Go ahead and pull that up. And the copy paste doesn't work properly for the spacing and everything for Medium. So if you see me hitting comments down every once in a while, that's why. So what we're going to do here, we'll just go ahead and run the chunk. We're going to require tidyverse and Lahman. You can use library if you want. Just felt like using require when I wrote this. If you get an error saying, hey, they're not found or something like that, all you have to do is uncomment one of the lines, and if you're on a Windows computer, you can have your cursor at the end, hit Control Enter, or if you are a Mac user, you can use Command Enter, same thing, and it'll run just that line. Make sure that you only install the package exactly one time. There's a chance that you can make R mad if you keep installing the same packages over and over and over and over again. It doesn't tend to like that. So for now, let's just use a comment to get rid of it if you need to run that. So once you've got the libraries written, that Lahman data actually has multiple data sets in it, and it's installed as a package. So what's cool about it here is that you don't actually have to download a file yourself or find a file and upload it or anything like that. It's all just within the package. So we're going to load the data for batting post as our data set. So batting in the postseason, it's about the World Series. And then we'll take a look at the first few rows. So we run that. We're going to get our data over here. And we've got a whole lot of variables. Right? There's a lot of things going on in here. And it goes back all the way to 1884. So, first thing we're going to do is probably need to filter out things away from 1884. So the next chunk of code is some of our filters. So turns out that one thing that we need to know is that the modern baseball is counted as modern after what's called the live ball era. If you want to take a look at what that means, Bradford Doolittle has an article on ESPN that's linked in the article itself that you can go take a look at and learn more about that era. So we're going to filter out where our year, in this case it's called year ID in the data set, we're going to filter that out for anything greater than or equal to 1920. And we're also going to filter for anything with the round WS. So that'll get just World Series in the live ball era. So we're going to create this object called slim batting post, and into that we're going to take our batting post data and use the pipe. This comes from tidyverse, where you have whatever you're taking in. Each time you have a pipe, you make your data smaller and smaller and smaller and smaller. Yes, I know we can combine filters and do 2 filters at a time. It's just more readable this way. But either way, we've got the data imported, and we've got a basic filter. I have this habit of using slim for a smaller data set. So we'll go ahead and run that, and our years start at 1920. We just have World Series. If you're ever worried about that, you can always do the summary of slim batting post $year ID. That would tell you the minimum and the maximum, and that's for a number. One of the things that I tend to do is you can do a summary parentheses as dot factor parentheses, and close that off and just look at the round, and we have 4,387 World Series, and that's it, right? So you can just double check that that's what we got real quick and move on from there. So sometimes one of the things that you can take a look at is if you ever need to know the rows of something, you can use the nrow function, and it'll tell you how many rows of data there are. That's more just for us looking at the data. The next thing that we're going to do here is set.seed. So I'm going to take another chunk here, and we're going to set the seed. So when you have your R environment and my R environment do not know what random is. R doesn't do real random, it does pseudo random, and it's based on the state of your machine at a certain time. So without a seed, your computer and my computer are going to have different states. It's going to have a different version of random. If we set a seed, and it doesn't matter what the number is, just any number, then that means that's where we're going to start figuring out what random is, and that way your random and my random are going to be the same. And that just ensures reproducibility. That's the whole idea. So after we've got the seed set, we're going to talk about testing and training data sets. So most people are of the school of thought that when you're doing simple machine learning like this, 80% of your data should be training, 20% should be testing. Some people think it's 70-30, 75-25, something like that is a good idea. Somewhere in that range makes sense. The whole reason that we split testing and training data, if you think about it, somebody comes up to you and says, hey, in 5 months, you have to know everything on this piece of paper, just memorize it, and you'll pass Calculus 3. So, if you just memorize what's on the page and the final exam is exactly what was on the page that you were given at the beginning of the semester, well, you're probably going to do pretty good on it, and you're probably going to get most of them right. If they give you that page and you just memorize how to do everything on that page but don't actually know how to do it, and they give you a different exam that has the same ideas just changed around, you have no idea what's going to do it. You're going to have a really low accuracy rate. So the idea is with training data, you learn how to actually do the thing. So that way, if you actually understand what's on your paper at the beginning, you can apply it at the end and have a pretty high accuracy score. That's the goal. So, we're going to take our training data out of the slim batting post object, and we're going to take the testing as well. And I'm going to copy paste this over here and format it so we can get the testing and the train together. Go ahead and break these down just a little bit so that it's a little easier to read. If you want to type these in manually at the beginning, it's probably a good idea. If you're more experienced, you should probably be doing just copy-paste style. But the first thing that I'm going to do is create an ID column. So one of the things that we've noticed about our data is that there's no easy way to separate these, right? Like there's nothing that's uniquely identifying everything in a single column. So we're going to create that column. We're just going to call it ID. It's going to start with 1 and be the length of the number of rows in the object. So that means we should be creating an ID column that goes from 1 to 4,387. To create the train data, there's more than one way to do this. This is just probably the easiest way, is to take our data, the slim batting post, pipe that into the sample frac function. So we're going to take a random sample of 80%. So I'm using 80% for training, 20% for testing. That comes from the dplyr package. So anytime in R you want to specify, I want to use this particular function from this particular library, put the name of the library followed by 2 colons and follow that by the sample frac or whatever function that comes out of that package. So we're going to have 80% of our data be training, and for our test data we're going to use another dplyr function called anti-join. And what anti-join is going to do is it's going to look at the data that we have for our whole object. We're going to look at the other object we want to compare against, so in this case train, and by ID. So this is why we created the ID column, so that way we can sort through, okay, well this number is in the original data but not in the training data, so it needs to go in test. That's the whole idea. And if we run those, we'll take a look at the output, just the first few rows, and it looks like they made it all good. We've got data here, we've got an output there, and we've got data there. So that's good. We can click on test, we can click on train. They both show up, passes the smell test. So now that we've got them split apart, what we can do is start figuring out what kind of model we can do. Now, there are a whole lot of different models that you can use. You don't have to use just generalized linear models, and realistically, it's probably not even the best model that you could use for this. So, one of the cool things that we can do is check the distribution. Most machine learning algorithms expect everything to be normal. Normal bell curve where you have a mean, standard deviation that has about 68% of your stuff, 2 standard deviations that have 95%, and whatever's on the tails. That whole idea, most machine learning systems want that. When you don't have that, you kind of pigeonhole one into the other sometimes, but when you don't have it, you need to tell your model I'm using a different distribution of data. So we're going to take a look at that and whether we need to do that by just quickly visualizing it. So the whole purpose of this article was to predict the number of home runs. All right, so what we're going to do is actually just look at the variable that tells that, which is the R number. So let's make a histogram, just like a basic histogram. We don't even need to bother with ggplot. It's not even worth doing. We just see we have a lot of stuff over here, about 1 and some at 2, but it starts off real high to the left, and then we taper off, toward not having any. So this looks like a pretty classic Poisson distribution, for the sake of having this. So we're going to have a lot more zeros and ones than we are sixes and sevens. So this does not look like a normal bell curve, so we just need to take that into account. So what I'm going to do here is, again, make a new cell, and we're going to paste all of that in. Now we got to kind of sort through the pasting here. Let's find out exactly where it's at, the fit all object. Okay, so we got that, and we'll put our summary, break that down to the next line. So we're going to have R as our dependent variable and everything else thrown in. So if you've never done GLM functions with R, or same thing with linear model, generally how this goes is you create an object name. In this case, I'm going to call it fit all, and into that we're going to use the GLM function. So your GLM function has a formula, it has data, and it has some kind of family term usually to tell you what kind of distribution of data there actually is. And so data equals train. We're going to use our training data to understand the variables, and we're going to use a Poisson distribution to tell it to do the math right. So now our formula here, we're going to have R is our dependent variable. R Studio and the R language in general has dependent variable, tilde, all of your independent variables. Right? So when you want to look at something that's your dependent variable and everything else that affects it is independent. So R is our dependent variable, and I've already selected all the terms that are numeric that are going to matter. So we can just start with that. All you have to do is just type in the column names. Don't use quotes. Just write them as they are, and make sure you define your data object. So if we go ahead and run that, we'll take a look at the summary. And we notice a few things here. So right off the bat, R gives us a ton of output. If you've never read one of these before, call is just the function that got run. That's just spitting back out to you what you put in. Nobody really worries too much about that. The deviance results, unless you just really love stats, I've never really had anybody care what those were. Coefficients, those where things get interesting. We have the intercept value, and we have all the stuff below intercept. So what we're trying to figure out here is, if you think back to 9th grade algebra, you have y equals mx plus b. Where the output of your thing is something times x plus an intercept. Like where your line runs into the graph. The intercept here is negative 1.5. That's where our line's going to start. And as we add more terms like G and AB and H and all this other stuff, as we start adding those in, if we have a value of 1 for G, we're going to start at negative 1.55, and we're going to do plus 1 times negative 0.05. And then we're going to actually have our line go down a little bit. If it's a positive number and we have a value that's positive, it'll go up. So you're just kind of modifying where your line's going to end up. So this is great. We care about the estimate column. Not a lot of people really care too much about the standard error column. And I've never had too many people say anything about the z-value. Those are just kind of statistical terms. What we're mostly interested in over here is p-values. So it's written a lot more complicated than that with this whole string of stuff. It's just our p-value. So when you think about a p-value, it's a number between 0 and 1. And the closer the number is to 1, the less sure you are that your result is not due to random chance. The closer to 0 you are, the more sure you are that your result is not due to random chance. So if we have a p-value of 0.05, what that means is we can be 95% sure that our result is not due to random chance. If we have a 0.99 p-value, we can be 1% sure. So if we're 1% sure that it's not due to random chance, it's probably due to random chance. So the numbers can get tricky, but you want to keep straight that it's, if you want 99% confidence, you're looking at 0.01 p-value. If you want a number that's 99.9%, then you'd have 0.001 or smaller. So we'll take a look at our p-values here, and when you're doing the stepwise regression method, what we're really worried about here is finding all the things that aren't statistically significant and taking them out one by one. So if we look over here at the p-values, we have something that's really, really, really small. If you write that number out, the way that, again, if you haven't seen this before, this 2e minus 16 means 2 times 10 to the negative 16 power. So what that's going to mean is 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 zeros and a 2. That is the smallest number that R is going to give you for a p-value. You know, that's what this actually means. So it's a really, 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 really small p-value. Same thing here with AB. You know, like that's this variable, whatever this means, is pretty statistically significant. When you have 3 stars, that means you can be at least 99.9% sure. When you have 2 stars, you can be 99% sure. So in this case, it's this 0.004316. Well, what that means is that we're smaller than 0.01, but we're greater than 0.0001. All right, so when we're here, that is 99% confident. When you have 1 star, that means you mean 95%. You know, this is smaller than 0.05, but it's still bigger than 0.01. Right, so we're like 95% confident. These periods over here, that means you're between 5 and 10% confident. Like you're not quite at 95, but you're almost there. Yeah, so some people accept those, some people don't. Generally, the rule is 95% sure or more. So anything with 1 asterisk, we're going to keep. Everything else, we're going to get rid of. Now, the interesting part about the stepwise regression here is, we're going to take things out one at a time. So I know in the article there's some other steps that it goes through. I'm going to get rid of this, but in the video here, I'm just going to work through the final version with you. So I'm going to go ahead and change the name, and I'm going to go ahead and change the name there as well. And we're going to run this. So it's going to be the same thing, but let's look here at what is our least significant term. If I can count, I would say that RBI looks like the least significant thing. It's 0.5, so we're less than halfway sure. So let's go ahead and just take that out. So we'll find where RBI is, and then we're going to just get rid of it and run it again. And our numbers, a few of them have changed. If you really want to go through, you can take a look at that on your own. But since this is the stepwise method, we're going to get rid of the next least significant thing. So we've got here, that's 0.26. That looks to be the biggest one, so x3b. We're going to get rid of that. And you guessed it, we're going to run it again. So what else we got? We've got a 0.18 down here at sh. If we can find it. There we go. We'll get rid of that and make sure we have our plus sign. We'll go ahead and run that. See what else we got. GIDP needs to go. Okay. And let's see, we've got a 0.1 going on here, so SF can go. And let's see what the next biggest one is. 0.08. Yeah, it's still not below our threshold of 0.05, so that's got to go. And we'll run that again. So again, in stepwise, we just do this over and over and over and over again until we get the answer. We've still got SO that's bigger, so we're almost there. And you do want to run it one at a time and not just take something out because it looks insignificant. It can change. All right, so let's go ahead and get rid of G. That's our last one. And there we go. So, especially something like, we didn't keep all of them, but you can take a look through all of your coefficients and your p-values and see what's changed over time. So this is going to be our final model. We have only statistically significant things left, and we have a model that works based on our training data. So now comes the fun part, where we are going to actually create some predictions. So fortunately, R has a really easy function to make predictions, creatively called predict. So I'm going to create an object here called predictions, and into that I'm going to use the predict function. I'm going to take my fit final, which was the one with only statistically significant numbers, and I know they'll probably be a little bit different than the article because I think this data might have been updated since I wrote the thing. But we're going to take that data, we're going to take our test data, and we're going to get a response. So when you use predict, this is saying what is the number that I want it to be. It's going to be a certain thing. And we're going to take the model and apply it to the test data and see how well we did here in a second. But we've made several predictions. All right, so the first few ones, we're telling whether we think it's 0 or 1 or 3 or whatever. And if we will look at the predictions over here, it's going to tell us what it thinks. So again, those are just going to spit out numbers. However, we want to be able to compare that to whole numbers. So we're going to have to put a few things together. So we're going to make a data frame, and we're going to do a little bit of selection and rounding. Here we go. And let's check our structure. So what we're going to do, we're going to create a new data frame called predict.df, and we're going to take all of our test data and our prediction data. And then we're going to create another object down here that it's called slim predict.df. So we're just going to select out of that, select from this object. We want year ID, round, player ID, team ID, R, and predictions. So now, and again, there's more than one way to do this. This is just an easy way to do it. We're going to create rounded predictions. So our numbers are going to be in decimal form, like you can see up here. They're all going to be in decimals. So we want to round them to 0 decimal places. So that 0.445 is going to be a 0. That 0.765 is going to be a 1. Those kind of things. So we're going to take that, and then we're going to do a Boolean value to see whether it's true or not. And we're going to see how well we did. So let's go ahead and run that. So remember, we have our predict.df, which is our test data set plus predictions, right? The next thing we made, slim predict.df. That is where we create our true-false match. What's our rounded prediction? Do they line up? So you see how this 1 in the rounded prediction is a 0. It's a false. This next one, it's a 1 and a 1, and we're going to be getting it true, right? So we want to deal with those because those are easy, and then we can have that data in there. The next step is we can get some basic results. Again, like if you want to do a confusion matrix, you can certainly do that too. But what we're going to do here with our results is take our slim predict.df, pipe that into a function to group them by TF match, which is whether it's true or false, and then we're going to pipe that into a summarise function to create a summary table of the counts of each. So if we run that, we're going to see that we have 292 falses, 585 trues, right? So that's how well we did. It's about 2/3. Not so bad for baseball. So one little trick that you can do at the end, sometimes you want to have an r² value, but if you notice in the GLMs, there is no r² value. You just have an AIC number. Your AIC number, again, is going to be the closer you are to 0, the better your model is. The further away you are from 0, the worse your model is. So, we want small AIC values. 6,500 is kind of big for most things anyway. So let's go down here and we will create ourselves a little bit of a linear model of the number of runs against our rounded predictions, and we'll get a nice r² value out of it. So we have a really significant relationship here, and our r² here is about 0.69. What that means, you can use multiple if you want. Adjusted is probably better for most people, but what r² means is it's the amount of variation of your dependent variable explained by all of the independent variables. So in this case, the amount of variation in R, 69.53% of it, is explained by the rounded predictions that we made. right? So those rounded predictions are going to inform us, and basically we're saying we got a 69%, right? So that's pretty close. Now, as far as where you can go from here, you can start doing confusion matrix, you can plot all kinds of things, we can do all kinds of things with it, but once you get the model to run and get some outputs and get it put in a data frame, life is usually pretty easy after that once you get into it. So again, this has been Tyler with ARIMA Security Research. Make sure you give us a like, sign up for the email list, head over to the website, check out some of the other articles, and until next time, we'll keep mashing buttons.